The SQL insert instruction allows to add data to a relational database. Here, you can see some examples. The first statement inserts a new tuple into the product table. The values are entered according to the order in which the columns have been defined using the create table statement. The second statement is equivalent, but also explicitly mentions the column names. This is recommended so as to avoid any confusion. The third statement adds 3 tuples to the product table. It is important to respect all constraints defined, such as not null, referential integrity constraints, etc., when adding new tuples to a table. Data can be removed using the SQL delete instruction. Here, you can see some examples. The first statement removes the product tuple with product number 1000 from the product table. The second example removes all supplier tuples from the supplier table where the supplier status is null. The third delete instruction includes a subquery. More specifically, it removes all product numbers from the supplies table of products that have the string heart as part of their product name. Obviously, this will remove the Chardonnay wines in the supplies table. Delete instructions can also contain correlated subqueries. This is illustrated in the fourth example, which removes suppliers from the supplier table that have no corresponding tuples in the supplies table. Here you can see 2 more examples. The first one is a self-referencing delete. It removes all supplies tuples where the purchase price is strictly bigger than 2 times the average purchase price for a specific product. The second example removes all tuples from the product table. As discussed before, the removal of tuples should be carefully considered as this may impact other tables in the database. Earlier, we spoke about referential integrity constraints which keep the database in a consistent state in case of removal of 1 or more reference tuples. Remember, the onDelete cascade option cascades the delete operation to the referring tuples, whereas the onDelete restrict option prohibits removal of reference tuples. Modifications to data can be made using the SQL update instruction. The first example sets the available quantity to 26 for the product number 185 in a product table. The second example, the second update instruction, sets the supplier status to the default value for all suppliers. The third example includes a subquery. It adds 7 days to the delivery period for all suppliers for all supplies of the supplier deli wines. Also, update instructions can contain correlated subqueries. This update instruction guarantees that supplier number 68 can supply all his products at the minimum price and delivery period. Here you can see a combination of an altered table and update instruction. The altered table instruction adds a column subcategory with default value silver to the supplier table. An update instruction is then used to set the values of this new column. In case the supplier status is between 70 and 90, a gold status will be assigned. In case it's higher than 90, it will be set to platinum. Remember, as with delete instructions, also update instructions can affect other tables in the database. Again, this will depend upon the onUpdate referential integrity constraints that have been set during table definition. We have now finished the discussion of SQL DML. SQL views are part of the external database scheme. A view is defined by means of an SQL query, and its content is generated upon invocation of the view by an application or other query. Hence, it is a virtual table without physical tuples. Views offer several advantages. They facilitate ease of use by hiding complex queries such as join queries or correlated queries from their users. They can also provide data protection by hiding columns or tuples from unauthorized users. Views are also a key component in a three-layer database architecture and allow for logical data independence. Views can be defined using the create view statement. Here, you can see three examples. The first view is called top suppliers and offers the supplier number and supplier name of all suppliers whose status is bigger than 50. The second view refines the first one by adding an additional constraint, subcity equals San Francisco. The third view is called Order Overview. It contains the product number, product name, and total ordered quantity of all products. Note the left outer join in the view definition to ensure that also products with no outstanding orders are included in the result. Once the views have been defined, they can be used in applications or other queries. The first query selects all tuples from the view top suppliers SF, which we defined previously. The second query retrieves all tuples from the order overview view where the product name contains the string chart. The database engine will modify queries that query views into queries on the underlying base tables. Here you can see an example. We have our view top suppliers and a query which uses it. Both query and view can be modified into the bottom query, which directly works on the supplier table. Some views can be updated. In this case, the view serves as a window through which updates are propagated to the underlying base tables. Updatable views require that insert, update, and delete instructions on the view can be unambiguously mapped to inserts, updates, and deletes on the underlying base tables. If this property does not hold, the view is read-only. Here you can see our view order overview, which we defined earlier. The update instruction tries to set the total ordered quantity to 10 of product number 154. Obviously, there are multiple ways to do this, and the RDBMS will generate an error. A view update is feasible when only one possible update on the base tables can accomplish the desired update effect on the view. In other words, this is an example of a view which is not updatable. Various requirements can be listed for views to be updatable. They typically also depend upon the vendor of the RDBMS. Common examples are no distinct option in the select component, no aggregate functions in the select component, only one table name in the from component, no correlated subquery in the where component, no group by in the where component, and no union, intersect, or except in the where component. Another issue may arise in case an update on a view can be successfully performed. More specifically, in case rows are inserted or updated through an updatable view, there is the chance that these rows no longer satisfy the view definition afterwards. In other words, the rows cannot be retrieved through the view anymore. The with check option allows to avoid such undesired effects by checking the update and insert statements for conformity with the view definition. Here you can see two examples of update instructions on our top suppliers view, which has now been augmented with a with check option. The first update will be rejected by the RDBMS. The reason is that the supplier status of supplier 32 is updated to 20, whereas the view requires the supplier status to be bigger than 50. The second update instruction will be accepted by the RDBMS, since the new supplier status is bigger than 50. Indexes are part of the physical database scheme. An index provides a fast access path to the physical data in order to speed up the execution time of a query. It can be used to retrieve tuples with a specific column value in a quick way rather than having to read the entire table on disk. Indexes can be defined over one or more columns. The syntax and implementation is RDBMS specific. Indexes can be created in SQL using the create index statement. Here you can see some examples. The first statement creates an index for the product name column, whereby the index entries are stored in ascending order. This index will be useful for queries retrieving products by product name. The second example creates an index for the supplier status. Indexes can be removed using the drop statement as illustrated. The keyword unique can be added to enforce that the values in the index are unique. Duplicate index entries will thus not be allowed. The last example is a clustered index, which stores the tuples in a table based upon the index key, which is supplier name in our case. Obviously, there can only be one clustered index per table, as the tuples can only be stored in one order. If a table has no clustered index, then its tuples will be stored in a random order. SQL also provides facilities to manage privileges. A privilege corresponds to the right to use certain SQL statements, such as select, insert, etc., on one or more database objects. Privileges can be granted or revoked. Both database administrator and scheme owner can grant or revoke privileges to, from users or user accounts. They can be set at account, table, or column level. Here you can see some popular privileges listed. Select provides retrieval privilege. Insert gives insert privilege. Update grants update privilege. This can be further refined by specifying column names. Delete gives removal privilege. Alter provides the privilege to change the table definition. References grants the privilege to reference the table when specifying integrity constraints. It can be further refined by specifying the column names that can be referenced. Finally, all provides all privileges. Note that most RDBMS vendors provide other specific options which you may want to check. Here you can see some examples of privilege statements in SQL. The first one grants select, insert, update, and delete privileges on the supplier table to user B bosons. The second example grants a select privilege on the product table to all public users. The third statement revokes the earlier grant delete privilege on the supplier table from user B bosons. As we already explained, SQL can be executed both in interactive as well as embedded mode. In what follows, we will elaborate on the latter. In fact, many RDBMS users are never directly confronted with SQL language constructs. They interact with applications, often GUI-based, which hide the underlying complexity of SQL. These applications are typically written in general-purpose programming languages such as Java, C, or COBOL combined with SQL statements. There are two broad options for using SQL statements in general-purpose programming language. In statically embedded SQL, the SQL statements are directly embedded in the host language. A popular example of this is SQLJ, which allows to embed SQL statements in a Java host program. In dynamically embedded SQL, the SQL statements will be passed as parameters of procedure calls using a call level interface. A popular example of this approach is Java Database Connectivity, or JDBC, which provides a set of procedures that allow a Java host program to communicate with a relational database. To successfully execute SQL statements in both settings, we need some additional language constructs for the interaction between SQL and the host language. The first important aspect concerns the use of host language variables in embedded SQL queries. A host language variable is a variable declared in the host language. They can be used in embedded SQL instructions to exchange data between SQL and the host language. A host variable used to pass database data to the application is called an output host variable. A host variable that is assigned a value by the application code, after which this value can be used in an SQL statement, is called an input host variable. Embedded SQL allows for host variables in any position where interactive SQL would allow for a constant. Because SQL is a set-oriented language, the query result will generally comprise multiple tuples. Host languages, such as Java, C, or COBOL, are essentially record-oriented. They cannot handle more than one record or tuple at a time. To overcome this impedance mismatch, the cursor mechanism was introduced. Cursors allow for the tuples that result from an SQL query to be presented to the application code one by one. First, a cursor is to be declared and associated with a query. After that, the cursor allows to navigate through the tuples that make up the result of the query and offer them one by one to the application. The cursor should be properly closed once the database processing has finished. As already mentioned, JDBC is a popular example of dynamically embedding SQL statements. Here you can see a high-level overview of how it works. The file myapp.java contains the Java source code of your database application. It uses the JDBC API to call the JDBC driver manager, which will select a vendor-specific JDBC driver to communicate to the underlying relational database. A key advantage of JDBC is that it provides a uniform access interface to various underlying data sources. Given its popularity, many database vendors provide support for it, such as Microsoft, Oracle, IBM, etc. It is also supported by MySQL. Here you can see an example of a Java program with JDBC statements. The program starts by importing the JDBC package by using the statement import java.sql.star. The first part of the code then sets up the connection with the MySQL database. The statement class.forName com.mysql.jdbc.driver dynamically loads the MySQL database driver. It is embedded in a try-catch block in case exceptions would occur. A scanner object is created to provide input from the keyboard. More specifically, we will ask to provide a supplier number for which information will be retrieved. The URL variable contains the location of the database scheme, and the username and password variables store the logon credentials. The query variable is a string containing the SQL query we wish to execute. Note that it is a simple query asking for information about a particular supplier for whom the number was provided using the keyboard. It includes one input host variable as indicated by the question mark. The statement connection equals drivermanager.getConnection URL username password establishes a connection to the MySQL database by creating a connection object using the logon information. In JDBC, all SQL statements are executed within the context of a connection object. A Java program can have multiple connections to different databases. The statement, prepared statement equals connection.prepared statement query, creates a prepared statement object based upon the query string variable. It needs to be further prepared by specifying a value for the input host variable. This can be accomplished with the statement prepared statement.setInt 1, subnumber. Remember, subnumber is the variable representing the supplier number we provided earlier. We can now execute the query and store its outcome in a result set object rs. It is important to note that in JDBC, all SQL queries are compiled and processed at runtime. The result set object contains a cursor pointing to a particular row of data in the result. Initially, it is put before the first row and can be moved using the method next. The latter returns false when there are no more rows in the result set. The while loop which follows now navigates through the results of the result set. The statement system.out.print rs.getString1 retrieves the first element of the row where the cursor is positioned and prints out the value. The other statements work similarly. To conclude the program, the prepared statement and connection objects are properly closed. Again, note that all these database statements are embedded in a try-catch block to accommodate any exceptions that may occur. Here you can see our JDBC program running in Eclipse, a popular IDE or integrated development environment for writing Java programs. You can see that we entered the supplier number 68 and our program returned 68, the wine depot, and 10. SQL statements can also be statically embedded in a host language. SQLJ is an example of this. It is built on top of JDBC and allows to embed SQL statements directly into Java programs. A preprocessor will then translate the SQL statements into Java or JDBC statements, which are then further compiled by the Java compiler to bytecode. The preprocessor can perform syntax checks, Java SQL type matching, and verifies the query against the database scheme at design time. This will not only result in fewer errors at runtime, but also improve the performance of the query. It is also a key difference with JDBC, where SQL statements are compiled at runtime. Note that, as illustrated in the figure, a Java program with embedded SQLJ statements should have a start.sqlj file name extension. SQL delimiters separate the SQL instructions to be processed by the precompiler from the native host language instructions. SQL's J statements start with a hash SQL delimiter and are terminated with a semicolon, as you can see illustrated. Note that each host language has its own SQL delimiter, as you can see here illustrated for C and COBOL. Here you can see an example of an SQL J statement similar to the query we used in the JDBC example. It has one input host variable, supplier number, and one output host variable, name. The example is a singleton select, as it will return only one value. In case of multiple values, a cursor mechanism needs to be adopted. Here you can see an example of a cursor, also called iterator in SQLJ. The iterator, mySubnameIter, is connected to the query select subnumber, subname, substatus from supplier. The individual rows can be retrieved one by one in a while loop using the method next. When compared to JDBC, SQLJ programs are usually more concise and thus easier to debug. As discussed above, SQLJ also allows to do syntactic, and semantic query checking at design time, in contrast to JDBC, where queries are verified at runtime. Despite its advantages, the SQLJ standard has been less popular than JDBC in the industry. As we have discussed in this chapter, SQL is a very powerful database manipulation language which allows to perform complex data processing operations directly in the RDBMS itself. When using embedded SQL, it is highly recommended to push as much as possible complex data operations to the database instead of the application program. This will not only facilitate program maintenance, but also improve performance, since every RDBMS has built-in sophisticated facilities for indexing and caching, which have a huge impact on query execution time. Hence, it is of key importance that an application developer working with an RDBMS possesses a deep understanding of SQL in order to write high-performing database applications. To conclude, in this chapter, we started by providing an introduction to relational database systems. We then discussed the data definition language part of SQL. This was followed by extensive coverage of SQL DML, or data manipulation language. More specifically, we discussed SQL select, SQL insert, SQL delete, and SQL update instructions. Next, we zoomed into SQL views, SQL indexes, and SQL privileges. The chapter was concluded by a discussion of embedded SQL, whereby we covered both JDBC and SQLJ.